Um, Imagine for a second you're sitting down at a super busy high-end restaurant.
Okay, I'm there.
So the waiter walks over to your table, notepad in hand, expecting your order. And you just look up, lock eyes, and say the word burger.
Just the noun, nothing else.
Exactly.
Yeah.
What exactly do you mean by that? Like, are you asking to see a picture of the burger on the menu?
Or are you, actually placing an order to have one cooked?
Yeah. Or maybe you're demanding they take the burger away because it's cold? Or, I don't know, maybe you're telling them to change the type of cheese on the burger they just brought you.
Right. There's absolutely no context.
Exactly. If you just shout nouns at a system,
Yeah.
communication completely breaks down. You need verbs to provide intent. You need actions.
And that exact same communication breakdown would happen, honestly, millions of times a second on the internet if we didn't have a strict shared set of rules for our digital verbs.
Right.
I mean, we'd have servers just panicking because they wouldn't know if you were trying to, read a database record or permanently delete it.
Which would be bad. Welcome to today's deep dive. Today, we are dissecting HTTP methods.
The verbs of the internet.
Yes, the invisible actions. These are the silent architectural verbs that keep the web from basically collapsing into unpredictable chaos.
They really are the foundation.
Because every single time you interact with the digital world, whether you're clicking a link or submitting a tax form or just doom scrolling the feed, your device is relying on this shared language.
Yep, it's happening constantly in the background.
So we're going to break down how these methods work beneath the surface, why some are considered inherently dangerous, and how, misusing them can lead to catastrophic database wiping failures.
Which happens more often than you'd think. But to set the foundation here, everything you do online ultimately boils down to 4 fundamental data operations.
Right, the basics.
Yeah, developers call them CRUD operations. That's CRUD, creating new information, reading existing information, updating what's already there, or deleting it entirely.
Create, read, update, delete.
Exactly. And HTTP methods are basically just the standardized way your browser tells a server which of those 4 things it actually wants to do.
Okay, but before we even get into the specific verbs, like the actual commands themselves, there's a massive dividing line we need to establish, right?
Oh, absolutely. The big split.
Yeah, because the architecture of the web sorts all these actions into 2 distinct categories based entirely on how they impact the server. We have safe methods and unsafe methods.
And that terminology is critical for understanding how web architecture actually flows.
So let's start with safe. What does that actually mean?
Well, when developers call a method safe, they mean it is strictly read-only. It doesn't change a single byte of data on the server.
Not a single byte.
Right. Think of safe methods like reading a book at a public library. You can pull the book off the shelf, right?
Yeah, I've got the book.
You can turn the pages, you can read the same chapter 100 times in a row if you want.
Okay.
But the ink on the page never changes. You are just observing the information, not altering it.
So you're strictly a spectator.
Exactly.
Okay, so the safe methods we're looking at are get, head, and options. And we'll explore the mechanics of those shortly, but let's define the other side. Unsafe methods.
Right, so unsafe methods are the actions that actively change the server's state.
They leave a mark.
Yeah, continuing that library analogy, if safe methods are just reading the book, unsafe methods are like taking a pen and writing in the margins.
Oh, wow.
You were adding new chapters, crossing out paragraphs, or burning the book entirely.
Defacing library property. Got it.
Exactly. And the main unsafe methods are post, put-t, patch, and delete.
I mean, I've always found that safe categorization fascinating, but let me push back on the framing for a second.
Sure, go for it.
If safe methods do absolutely nothing to change the server, why do we care about them so much? If they are completely passive, isn't the real action happening with the unsafe methods?
It's easy to think that, actually, but retrieving information, reading the book is arguably what drives 95% of internet traffic.
Oh, I guess that's true.
Yeah. I mean, you're reading the news, you're streaming a video, loading a weather dashboard. It's all reading. But more importantly, because a server knows an incoming request is mathematically guaranteed to be safe, it can treat that request with far less caution.
Less caution. That sounds bad.
It sounds bad, but that lack of caution is actually the secret to web performance.
Oh, really?
Yeah, it allows the infrastructure to cache data, copy it to edge servers globally, and, deliver it to you in milliseconds, completely knowing the action won't accidentally corrupt a database somewhere.
Okay, so the safety is what allows the speed. That makes sense. And that takes us right to the two absolute heavy lifters of the web, the methods powering almost everything you do. Get T and post.
The big two.
Right. So Get T is the ultimate safe method. It's the browser saying, show me this web page or send me this image.
It really is the workhorse of the internet. Because Get doesn't alter state, it unlocks all those architectural shortcuts we just mentioned.
Like the caching.
Exactly. Browsers will cache a massive background image delivered via a GET request, so they just don't have to download it in tomorrow.
That saves a ton of data.
Yep. Plus, you can bookmark a GET request, you can copy the URL and text it to a friend, and they will see the exact same thing you see.
Now wait, I've noticed something. Like when I'm on an e-commerce site and I filter a massive list of products.
Okay, yeah.
Say I'm looking for a very specific model of red running shoes in a size 10. The URL changes, right?
Oh, yeah, it gets really long.
Yeah, it gets all those weird symbols and text tacked onto the end of it.
Yeah.
But I'm interacting heavily with the store's database to find those shoes. Am I still just using a GAT request?
You are, actually. That's a perfect example of how flexible GT can be.
Really, even with all that extra junk in the URL?
Yep. Those extra text strings at the end of the URL are called query parameters.
Yep.
You are essentially sending a highly specific set of instructions to the server's database, asking it to, filter, sort, or paginate its inventory.
But it's still safe.
Fundamentally, yes. You are still just asking it to show you information. You haven't actually bought the shoes. You haven't changed the store's inventory.
Oh, I see.
You're just window shopping with a very, very specific magnifying glass.
Okay, I love that.
Yeah.
Window shopping with a magnifying glass. So if GT is window shopping, then POST must be walking into the store, bringing the shoes to the register, and actually swiping your credit card.
That is the exact transition point from safe to unsafe, yes.
Okay, so POST means making a change.
POST is the method used to submit data to a server to create a new resource or trigger a state change.
Like filling out a form.
Exactly. When you fill out a registration form, upload a high-resolution photo, or click that Confirm Order button at checkout, your browser bundles all that information into a POST request.
It hands it over.
Right. You are handing a package of data to the server and saying, hey, process this and create something new.
And because it's creating something, it's inherently unsafe. It's altering the reality of the server's database.
It's triggering back-end logic, which is risky. It might be deducting funds from your bank account, or initiating a shipping sequence in a warehouse, or even just blasting out an email confirmation. Because the stakes are so much higher, browsers handle POST requests with extreme paranoia.
This actually explains a wildly frustrating experience I think we've all had.
Oh, yeah. Which one?
So I can be on a news website reading an article, right? And I hit the browser's refresh button 50 times in a row, and nothing happens. The page just reloads instantly.
Because it's a GET request.
Right. But if I'm trying to secure tickets to a sold-out concert and the checkout screen stalls, I panic, I hit refresh, and the browser suddenly throws up this terrifying warning box.
Ah, the classic confirm form resubmission pop-up.
Yes. It practically begs me not to proceed. Like, are you really, really sure you want to do this? Why this sudden intervention?
Well, because your browser understands the HTTP methods being used, even if you don't realize it. That warning box is entirely about retry behavior.
Retry behavior.
Yeah. Retrying a GET request on a news article is totally harmless. You're just asking the waiter to see the menu again.
Sure. No harm done.
But if you hit refresh on a stalled checkout page, you are asking the browser to resend that exact same bundle of POC data.
Oh, I see.
The browser intercepts you because it knows POST is an unsafe, state-changing action. It's basically warning you, hey, if I send this again, you might accidentally buy those concert tickets twice.
Oh, wow. So the browser is acting as a safety net against the architectural danger of the POC method.
Exactly. It's protecting you from yourself.
Okay, so we've pulled data with GET, and we've created new records with POs. But what happens right after you submit that POST request?
What do you mean?
Say I create my account, but I realize I fat-fingered my email address and made a typo. I need to fix a single letter. I'm not creating a new account, and I'm not just reading it. I need to update it. How do the verbs handle that?
Okay, so this is where we run into the complexities of data updates. The architecture gives developers two distinct methods for modifying existing resources, PUT and PAT-TH.
PUT and PAT-TH.
Okay.
Both are heavily unsafe because they rewrite existing data. But the mechanics of how they rewrite that data couldn't be more different.
How so?
Well, PUT is the older, more established method, and it is, frankly, a blunt instrument. It requires a complete, full resource replacement.
A blunt instrument. Let's map that out.
Okay.
If my user profile in a database consists of my first name, last name, home address, phone number, and this newly typoed email address, if I use a PUT request to update just the email, what does that data package look like?
If a developer wires that update using PUT, they cannot just send the new email address.
They can't.
No, they have to pull down your entire profile, change the email locally on their end, and then send the entire profile back. First name, last name, address, phone, and the new email.
That seems like a lot of extra work.
It is. PUT basically tells the server, take this entire package I'm giving you, find the existing file, and completely overwrite it. Wait, what if the developer makes a mistake? What if they just send the PUT request with the corrected email address, and they just leave out the name, address, and phone number? Does the server intelligently merge them?
No. And that's the real danger of PUT.
Oh, no.
Yeah, the server blindly follows the protocol. It assumes the new tiny package is the complete truth.
So if you leave the phone number out,
If you leave the phone number out of the PUT request, the server assumes you want your phone number erased. It overwrites your robust profile with just an email address, wiping out everything else.
that feels incredibly fragile. It's like demolishing the entire foundation of a house just to repaint the front door. Why would we design a system like that?
Honestly, it guarantees predictability. You always know exactly what the final state will be. But you're right, it's highly inefficient for large data structures.
Which brings us to PATCH.
Exactly. That's why the PATCH method was introduced later on. If PUT is a sledgehammer, PATCH is a scalpel.
So with PATCH, I only send the new email address.
Precisely. You send a tiny payload that essentially says, hey, leave the name, address, and phone number alone, but replace the email string with this new one.
That makes so much more sense.
It's a partial update. It saves massive amounts of bandwidth and reduces the risk of accidentally wiping out unrelated fields.
It sounds much safer.
Well, careful with that word. Don't let the precision fool you. Because it alters the database, PATCH is still strictly classified as an unsafe method.
Ah, right. The scalpel can still do damage.
Exactly.
All right, so we've covered creating, reading, and updating. That leaves the final primary operation, removing things entirely.
The big D, delete.
Right. And alongside that, I really want to dig into some of the invisible, behind-the-scenes methods that keep the web secure. So let's talk about delete, head, and options.
Okay, well, delete is exactly what it says on the tin.
No surprises there.
No surprises. You want to remove a photo, destroy a database record, or terminate a session. You send a delete request. It is obviously unsafe.
But there's a fascinating quirk about delete. With post, we established that retrying the action is incredibly dangerous, right? You might buy the shoes twice.
Right, double charging.
But our sources say retrying a delete request is generally considered safe from a system state perspective. Why the difference?
It comes down to the concept of the final outcome.
The final outcome.
Yeah. If you accidentally fire a post request twice, the server creates two distinct orders. The state changes twice.
Yeah.
But think about delete. If you send a delete request for an image, the server deletes it. The state changes.
Okay, the image is gone.
Right. Now, if a network glitch causes your browser to send that exact same delete request a second time, like a millisecond later, the server looks for the image, sees it's already gone, and does nothing.
Oh, I get it.
Whether you send one delete command or 1,000, the final reality on the server is identical. The image is gone.
The outcome is locked in after the first success. That's really clever. Okay, let's pivot to the invisible helpers. I say invisible because, as an everyday user, I never actively trigger these, but they are constantly firing in the background.
Oh, they're essential.
Let's start with head. Our notes say it acts exactly like a JIT request, but it returns no body, just headers. What is the actual utility of that?
The utility is, frankly, immense bandwidth savings. Think of headers as the metadata of the web. It's the information about the file, not the file itself.
Okay, like what?
Like how big is it? What date was it last modified? Is it a PDF or an MP4?
So it's like walking into a grocery store, picking up a massive box of cereal, and just reading the nutritional label on the side without actually opening the box or eating it.
That's a really great way to visualize it. Imagine your browser needs to download a 50 gigabyte 4K video file.
That's a big file.
Yeah. If it uses GitT, The server immediately starts blasting all 50 gigabytes across the network. But what if the browser only wants to check if the file format is compatible, or if the file has even been updated since yesterday?
So it asks for the label first.
Exactly. By sending a head request, the browser gets the nutritional label back in just a few milliseconds. It reads the file size and the modification date safely. If it decides it actually needs the file, then it commits to the heavy get to request.
It's a scouting mission. I love that. Now, what about options? I see this method tied heavily to security and something called pre-flight checks. Why does a browser need to ask for options?
It's all about trust.
Shouldn't it just attempt an action and wait to see if the server rejects it?
But attempting the action is exactly what hackers want you to do. This brings us to a critical security concept called CORS, C-O-R-S, cross-origin resource sharing.
Okay, how does that fit in?
Well, modern web applications are heavily decentralized. You might be on a website located at domain A, but the code on that page is trying to send a complex POST request with your sensitive data to an entirely different server at domain B.
Right, like a storefront trying to send my credit card details to a Stripe API server to process the payment.
Exactly. But domain B doesn't know who domain A is. If the browser just recklessly fires that unsafe POST request across the internet, the server might panic.
Or get hacked.
Or worse, yeah, it might process malicious data before realizing it shouldn't have. So the browser intervenes, it pauses the transaction, and quietly sends a safe options request to domain B first.
Wait, so it's basically walking up to the bouncer at a nightclub and checking the guest list.
That is exactly what CORS is doing. The options request asks the server, hey, I have a client on domain A trying to send you a POS request. Do you allow this?
And the bouncer checks the list.
Right. The server checks its CORS policy. If it replies, yes, domain A is on the list and POST methods are allowed, the browser gives the green light and the actual data is sent.
What if it says no?
If the server says no, the browser blocks the data from ever leaving your device. It prevents a massive amount of cross-site forgery and broken data states.
So the browser is constantly negotiating with bouncers in the background just to render a modern web page? That is wild.
It's a dizzy place under the hood.
We know the verbs now and we know the security checks. But theory is one thing, reality is another. Let's look at how these methods collide with the actual physical code of the web.
Yeah, this is where historical baggage makes things pretty complicated. We've talked about get, post, put t, patch, and delete. But if you look at standard HTML,
The core markup language.
yeah, the language used to build text boxes and submit buttons since the early 1990s. HTML forms only support get-t and post natively.
Wait, the fundamental building blocks of the web don't support deleting or updating.
Nope.
If I want to build a simple web page with a button that updates my user profile using PUT, I can't just type that into the HTML.
You cannot. When HTML was designed, the web was mostly static documents. You fetched a page with VGT or you submitted a basic form to a server with post. Complex APIs just didn't exist yet.
So how did developers use the other verbs?
To use putty, patch, or delete today, developers actually have to layer JavaScript over the top of the page. They use modern tools like the Fetch API to intercept the form submission, override the browser's default behavior, and manually construct the putty or delete request in the background.
That historical limitation has to be the root cause of so many sloppy coding practices.
Oh, you have no idea?
I mean, if UT and POST are the only ones native to standard HTML, developers must constantly try to bend them to do things they weren't designed for.
They do it all the time, and it leads to massive architectural failures.
Give me an example.
Well, a very common mistake is using a POST request just to fetch data. A developer might write an endpoint like POST get inventory simply because they want to send a complex, secure data payload in the body of the request instead of putting it in the URL.
But we know KeyOT is an unsafe method designed for creating things. If they use it just to read the inventory, what breaks?
Everything built on the assumption of safety.
Ah,
Yeah, the browser won't cache the inventory list, so the user has to download it fresh every time. Content delivery networks won't optimize it. But the biggest casualty is search visibility.
search engines, like Google.
Exactly. Search engine bots are programmed to build an index of existing knowledge. They do not click submit on forms, they don't buy products, and they absolutely do not send POST requests.
Oh, I see.
If you hide your data behind a POST method to Google, that data simply doesn't exist.
You're basically locking the library doors and wondering why nobody's reading your books.
Perfect analogy.
But there is a mistake that is far more terrifying than poor SEO, isn't there? Using a DIT request to trigger a deletion.
Oh boy. Yes.
What happens if a developer, maybe trying to avoid writing complex JavaScript, simply creates a standard HTML hyperlink that says DET delete user account 10?
This is the ultimate nightmare scenario of misusing HTTP verbs. We established that the entire architecture of the web trusts ET to be completely safe, right?
Oh, it's just reading the book.
Right. And browsers eagerly preload GET links in the background just in case you decide to click them so the page feels faster.
Oh, I see where this is going.
It gets worse. Think about how search engine crawlers work. A bot from Google or Bing lands on your site, and its sole biological imperative is to discover and click every single GET link it can find to index the content.
Because it assumes they're safe.
It assumes those links are just reading the book.
But the developer wired the links to be landmines.
Yes. If a search engine bot arrives on an administrative dashboard where clicking a standard link deletes a database record, that bot will systematically click delete user 10, then delete user 12 at a speed of thousands of clicks per second.
That is horrifying.
A helpful, completely innocent search bot will effortlessly vaporize your entire database simply because the developer lied to the web architecture about what verb they were using.
The robot is literally just doing its job, reading the pages.
Mm.
But because you tied an unsafe action to a safe verb, the whole system collapses.
It's a disaster.
That really drives home why this framework exists. It's not just semantics, it's the physics of the web.
That's exactly right. HTTP methods are the contract between your application and the entire internet infrastructure. Get is for reading safely. Post is for creating. Put and patch are for precise updating. Delete is for removing. Respecting those verbs guarantees the ecosystem works for you rather than against you.
It changes how you see the digital world entirely. Next time you're interacting with a smart home device, I want you to think about this unseen language.
Yeah, it's everywhere.
When you shout across the room and ask your smart speaker to turn off the living room lights, what is happening in the micromilliseconds after? Is the device sending a PATSY request to a server just to update the status of the light bulb from on to off? Or is it firing a post request to trigger an entirely new action sequence in your house?
It's all verbs.
Even the physical world around you is now being controlled by these invisible digital verbs.
So true.
The internet is always listening, so make sure it understands the action you're trying to take. That's our deep dive for today. Keep thinking about those unseen verbs, and we'll catch you next time.